GCSE Physics boosters, the generator effect. In the last video we talked about the motor effect. This is pretty much the opposite. This is the generator effect. And this picture, it's a wind-up radio. Now, here's a magnetic field. Okay, we've got a couple of magnets, north-south. It's called an eclipse magnet. And basically it's producing a uniform magnetic field. Now what we're going to do is we're going to put a wire in this field and we are going to move the wire. So we're holding the wire and we are going to move the wire. We are going to make it move. Okay, so you see here, there's me holding this piece of wire and the ends of the wire are connected to a voltmeter. Now, when the wire isn't moving, nothing happens. We don't get any voltage. When we move the wire, then we get a voltage. Okay, so we move the wire down and we create a voltage. If we move the wire up, then we get a voltage in the opposite direction, like positive, negative. Okay, and that is the generator effect. So we are doing the work and we are creating electricity. It's the generator effect. The faster we move the wire, the bigger the voltage that we get. And as I said earlier, when we move the wire up, then the needle moves the opposite way. So in the last video, we talked about the motor effect, and that's electrical energy changing into mechanical work or kinetic energy. Now this is the opposite. Yeah, it's the generator effect and it's mechanical work or kinetic energy changing into electrical energy. I'm making a big point of this because a big mistake students make is they get them muddled up. So try and, devote a different part of your brain. One is the motor, one is the generator. And if you get an exam question, is it a motor? Is it a generator? Don't get them muddled up. Now, this is a very wordy little thing. I'm going to explain it on the next slide. When a conductor moves relative to a magnetic field, or if the magnetic field around a conductor changes, then a potential difference is induced across the conductor. If there is a complete circuit, then a current is also induced. That's a bit of a mouthful. What's all that mean then? Well, so when a conductor moves relative to a magnetic field, so either the field moves or the conductor moves, or if the magnetic field around a conductor changes, if it gets stronger or weaker, then a potential difference is induced across the conductor. To induce something means to make it happen. A potential difference, a voltage, is induced across the conductor. And if you have a complete circuit, then you can also get a current. Now, when a conductor moves relative to a magnetic field, so we've just seen moving a wire in a field, or rotating a coil in a field, which is what happens in a generator. Or if the magnetic field changes, so if we move a magnet in and out of a coil, we're going to look at that in a sec, or in a transformer, and I'm going to do a whole video about transformers, then a potential difference is induced. We create a voltage. Now, we always get a voltage, we don't always get a current. To get a current, you need a circuit. So if you look at the diagram, without the bulb there, there's no circuit. We get positive, negative, we get the voltage. When the bulb is there and we have a circuit, then we also get a current. Yeah, you can have a voltage without a current, but you can't have a current without a voltage. So it's quite a mouthful, there's a lot to it, but that is the generator effect. Now, this is an excellent simulation, which I can't take credit for this one, and it's Faraday's Law. It is a FET simulation, Okay, check out these PhET simulations, they are brilliant. And what you can do is, here, look, I'm moving a magnet in and out of a coil, and you see what the bulb is doing, it's flashing. Oh, look, when I do it faster, we get a bigger current, we get a bigger voltage, a bigger current. I can put a voltmeter in there. Yes, and you notice when I move it in and out, the voltage goes one way and then the other way. I can also flip round the magnet to see what difference that makes. And I can also add some field lines to it as well, some magnetic field lines. Okay, so the size of the voltage depends on the relative speed. It depends on the strength of the field, in other words, the strength of the magnet. It depends on the length of the conductor. In this case, that would be the number of turns on the coil. Then whether the voltage is positive or negative will depend on the direction of the motion and the direction of the field. Okay, it's a free download. These PhET simulations are free and they're very, very good. Check it out. Do some Googling. Here are some generators. There's a bicycle dynamo. That's a little one, but it does its job. The middle one is something that you might find on a building site, generating electricity. And then the one on the right is in a power station, big, massive generators in a power station. And a generator is basically a coil or several coils rotating inside a magnetic field. And we get an alternating voltage. We get an AC voltage as the coil rotates. Finally, now this is a little bit tricky. It's due to something that at A level we do it called Lenz's law. You don't need to know that it's called Lenz's law. But anyway, let's go through it. So if you drop a magnet, so get hold of a magnet and drop it, then it just falls, okay, like a stone. If you drop a magnet through a coil, then something interesting happens. Drop a magnet so that it falls through a coil which has a bulb connected to it. Now, the magnet takes more time to fall, so something must be trying to stop it from falling. The magnet takes more time to fall and the bulb flashes. If the magnet is strong enough, if you have enough turns, then the bulb will flash. More likely to flash if it's an LED. Any idea why? So, why? Well, the bulb flashes, and that's just basically the generator effect. We're inducing a voltage, we've got a circuit, so we're inducing a current, so that's just the generator effect, okay? Now, this induced current will produce its own magnetic field. So now we have two magnetic fields. We've got the magnet's magnetic field and we've got the coil's magnetic field. Now they will oppose each other. Yeah, the magnetic field of the coil opposes the motion of the magnet. Just like friction, it tries to slow it down. Now, why does it try to slow it down? Well, basically because something has to do work. This bulb is flashing. We're getting energy from the bulb. Where is the energy coming from to light the bulb? and it must be the work done by these two fields opposing each other. It's a little bit tricky, but if you remember that top sentence, the induced voltage current always opposes the change that produces it. Another way of thinking about it is, to make electricity, you have to do work. Okay, you have to do work to make a generator produce electrical energy. Okay, and to make you do work, then the induced current will produce a field that tries to stop you, to try and slow you down. Okay, if you look at this diagram, this is a small generator, and we're charging up a mobile phone. Now, where does the energy come from? It has to come from somewhere, and the answer is that it comes from you, because you have to do work cranking that little handle. And to make you do work, the two magnetic fields oppose each other, just like friction.